Okay, hi everyone. We are doing a working session talking about multicomputation and its implementation in Wolfram language. And so last time, one of the things that we had evolved to is the question of when you're operating. I mean, we've got several different things going on. Maybe is this new, or is this what we saw before, Nick?
Is what we saw before.
Have you been completely quantum since we last looked at this stuff?
Well, I did a little bit work on patterns.
Ah, okay.
Like, it's not complete yet. There's some difficulties here.
Do you want to talk about that? I mean, you're talking about pattern manipulation functions.
Yeah, like find pattern instance, subpattern instance, but it's very unclear. I need some more time to figure out stuff.
You know, I was just looking at some to-do lists from 5 years ago, and one of the things that was on there was this thing that just says match list or matches list, which is the thing we talked about last time of just showing the bindings for pattern variables and so on. I don't know whether you, I mean, that's a very straightforward thing that I think we should have. Okay, but so let's again refocus on what we think we know about what's happening here. I mean, we've got, you know, on the one hand, we've got evaluation graphs, and that's Ian. Do I have some notes here? Let me see. Do I have notes? Oh yeah, I have tons of notes here. Wait a minute. We've got a 22. Wait a minute. We've got this to-do list, right? I don't want to repeat this again. Okay. So we've got first these things for pattern manipulation. And basically, Nick, you say you're working on these. Is that right?
Well, yeah. Some of them are quite unclear exactly what they should do.
Okay, well, let's talk about
it. For example, with the pattern, especially when there's some weird pattern primitives like accept. So you have to, if you want to come up with the instance of accept, it's like some kind of finding a negative pattern. And how that would play out, I don't know.
Okay, well, so wait a minute. Find pattern instance. So let's say accept 0. What do you generate for that pattern instance?
Well, I would generate just, well, first of all, I want to distinguish between like an expression and a pattern. Like a pattern is any expression that has at least one primitive, pattern primitive, like one of those verbatim, alternatives, accept, whole pattern, whatever, blanks. So, and pattern instance not necessarily produces an expression without patterns, pattern primitives. It just kind of lowers their quantity, kind of go one level down of pattern hierarchy in some way.
Why is there a hierarchy?
Well, because, for example, you can have an expression that, for example, in alternatives, you can have another pattern primitive, like another accept alternatives. Well, alternatives is flat, but maybe some other pattern primitive. So basically, you can enumerate patterns themselves.
Why do we think find pattern instance is useful? Other than for sort of pedagogical purposes?
Yeah, that I don't know.
So
the most useful function is unifying expressions and patterns. So if they don't have any named patterns, so what is the unification gonna do? So like if there's some named pattern and there's a way to substitute it with some expression so the two patterns become equal, then that's useful. But if there's no named patterns, and there still can be some unification.
Okay.
And maybe you could produce some sort of way of addressing the different, the different sort of all the blanks, all the pattern primitives that got replaced, and like you use their position, if you know what I mean.
I think this is a general feature because we got to, one of the things we got to know here is the what happened in a replacement. That's a thing that we're going to need for many purposes, right? me just save this in the right place. Okay, so this is about patterns. Okay, so I mean, again, what we already think we need, and I don't quite know why it's not listed here, is is all the stuff to do with you know, matches list and so on, or something, whatever that's called. Right, the thing that tells us, you know, I don't know exactly which way around it is, but let's say x blank, comma, f of 6, 6, and that would go to, you know, I think we talked about this last time, did we not? Can somebody remind me?
I pointed out that multi-replace without right-hand side of rules basically produces a match list.
Okay. Well, so, but I think we need this function, and the point that you made previously is it can have multiple results, correct?
Yeah, there are multiple ways of doing it. By the way, in the agenda, I also included this concept called multiness. It's like all possible ways, like in the end, all possible ways that there can be multiple results when you're doing a substitution.
Okay.
There are three fundamental ways to having those.
Okay. And so, I mean, that's related. Okay, that's again, zoom out. I mean, the things we're trying to achieve, as we've been talking about for many times here, are these things here. These are kind of endpoints that we want. Now, yes, and we've also talked about, okay, so let's again go through, did we make any progress on find replace path, find equational path? For those,
No.
progress, no progress.
I mean, I don't want to speak on behalf of Nick, Stephen, but I don't think much progress has been made on this at all. It's going to be made after the summer school.
Yeah.
Okay.
So my
That's what we discussed.
sure.
That's
The
what we
proof
agreed
object,
upon.
the proof object is kind of in the process, and those things are related to those. At least find equational path.
Okay, so what's happening with proof object?
Well, there's some disagreements. the
Okay, well,
pull
then this
request
is
is there.
Then this is a good meeting to discuss it. Can somebody explain what the disagreement is?
Oh, I guess I can. So
I can also, if you want.
okay, go ahead.
Yes, so I think there are two types of disagreement. We discussed in the last meeting the structure part, and we agreed on how to do that. And then there is the other part, which is that the proofs have changed a lot, because the proofs are now by contradiction. The result is, in my opinion, rather strange, which it may be fine. It's actually faster, which may be good, but the proofs are kind of much simpler to the point that I find them difficult to understand.
Okay, can we see some examples? Nick, do you want to share, and can we look at some examples?
Okay, give me a minute.
Okay. So, I mean, clearly, whatever find equational proof does and has done for the last however many years, it has to keep on being able to do. So whatever we're adding must be a different path, right?
Right. I think we could, for example, add an option, and then the user specifies whether a direct, an explicit proof is wanted, or perhaps a contradiction proof is wanted.
Why is a contradiction proof easier to do?
That I don't know.
Well, because it's much shorter in general, because you don't have to. Well, it's not the fact that you're doing contradiction, it's the fact that your variables. It's like you're trying to find variables instead of like explicit constants. Because basically it's how Waldmeister works. It's not even the proof itself. I don't know. Because like I can explain.
Okay, well,
it
let's look at an
completely.
example. When you're ready, let's look at an example.
Yeah.
Okay. So there's a question for Ian while you're getting ready, Nick.
Mhm.
The evaluation graph stuff. How has that developed?
So there's an internal documentation page for trace graph. And I need to submit that to the function repository.
Okay. And so, okay. So this is, so what you've actually done is trace graph.
Yeah.
And that takes the same arguments as trace, is that right?
Mm-hmm. All the options and arguments of trace.
Okay. Well, I'd love to see that actually. What can you submit that to the function repository sometime really soon?
Yep.
Okay.
The documentation should be in CVS. If you want to look at it now.
Yeah, how do I get to it? Do I go through Docker Tools or some other way? So it's there as a system function? I mean, a system function documentation or what?
Right, it's in the trees context.
But we imagine initially this is going to be put in as a WFR, is that correct?
Yeah.
Okay.
And maybe become system.
Okay. And do we think we resolved the major? Can I run this, by the way?
Yep.
How do I do that?
It's in 13.1 in the trees context.
Oh, snazzy. Okay. Hold on. So I just say trees backtick this.
Yep.
That is uninspiring. What did it do there? Well, there's two
Are you
big.
sure you don't need to do, sometimes with packlets, if you use a symbol that isn't one of the explicitly exported symbols, it won't load the whole packlet correctly.
So I know I made a lot of changes to the tree visualization code that this used. May have introduced a bug.
Okay. Well, can you track that down? But I mean, so here, let me try something here. I'm very interested indeed to see something here. Hold on one second. I need to find something. Do you know where I put? Hold on. I can find this. Oh no, this isn't the right thing.
Yeah, unfortunately, this is broken.
Is it totally broken? Can you make sure it gets fixed? I mean, does it have the right structural form or not?
Yes, it's just the vertex shape function.
Sorry, is there somebody? Let me just see. For some bizarre reason, the files to do with our upcoming summer school project list have disappeared from the place where I put them earlier today. So that's a problem that maybe Kristen can go chase.
Yeah, I'll ping Danielle about that. Yeah.
It's kind of like not good at all. Okay, what I'm looking for are those crazy nested recursive functions. Did I try that test before? I'm not certain if I did. Let me see, I can find one, I'm sure. Hold on one second. Oh my gosh, where did I put this? I'm pretty sure I had an example. There's a great one of these nested recursive functions. Oh, drat. Oh gosh. Okay, hold on. Here we go. This is the function, although it's full of gunk here. Okay. This is it. I can get rid of the so's. Yeah, just get n minus 1. Why that 1 is there. N minus f of n minus 1. Is this really right? I don't know if this is right. Well, let's try that. Okay. 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 Let's try this if that works. Oh, come on. Is this just completely broken? Ian?
The structure of the graph is correct.
Well, I don't think it is.
Style, it's wrong.
I don't think it is correct.
Do trace original goes to true.
In here?
Mm-hmm.
So if how would I get rid of all that gunk to just see the structure of the graph?
Label tree.
I'm sorry?
Unlabeled tree.
Is it a tree?
Not a tree.
Well, if I just say graph,
Oh, no, this is a graph. Of course. Sorry.
Like shape function goes to automatic, maybe.
why isn't the automatic top of the autocomplete list there? Okay. Oh, this is cool. This is really cool. Okay, hold on. Let's just do a slightly smaller one of these. Okay, have I done this before? I have a tremendous sense of deja vu here. I mean, this is some kind of something must be wrong here. No, I don't understand this. I'm doing. Does this have a memoizer? Oh,
Yep.
stupid. It has a memoizer. Forget that. Okay. Without memoization. Oh my gosh, that's already that complicated. Oh, it may go to negative values. This is really cool. So, I mean, this is a recursive evaluation. This is a non-trivial recursive evaluation showing, and now what I should be able to see here is different forms of recursion, both reevaluation recursion and sort of recursion through the expression. How do I see that in, so let's just try f of 1 here.
So the dashed red lines are where a transformation rule gets applied.
Okay.
And the solid edges are for subsidiary evaluations.
Okay. So f of 0 better be trivial. That just better go. I don't even understand why that goes through so much conniption to get to its result. Now, if I just say trace the f calls, is that going to work, or is that going to be?
Yep. You can do the symbol F or a pattern.
Oh, that's weird. Is that obvious? That it always has to be kind of like a single, well, let's try something like f of 3. That's really weird. Is that obvious that that has to work that way? Let's
Can
look
we
at
see the actual trace?
Yeah, but look at what this is doing. This is going. Yeah, we can see the actual trace. I don't understand. Because this should show sub-expression evaluation, right? Which shouldn't be looking like this. There's re-evaluation, so to speak, and then there's sub-expression evaluation. I don't understand how this could possibly be right.
Well,
And can
So
you remove the F?
expression evaluations because of all of the layers of nested lists, but they don't contain anything other than Fs because of the pattern.
I understand that, but what we are trying to show in the trace graph is the difference between, in here, it's going to do the sub-expression evaluation here. That's separate. I'm really confused. Why is it just linear? Do you think it's right that it's just linear?
In this case, yeah. Look at the next thing after that expression in the trace is that big nested list. And then there's nothing after that.
I'm sorry, what are you saying in the traces? Well,
You
okay, so if I say
F of
this,
1 minus F of 1 minus 1. Yeah.
Quite my point of view. So wait a minute. Those are with the pluses, but with F alone, what are you saying? I don't understand why this F of 3 doesn't have a sub piece evaluating F of 3 minus 1.
Well, the F of 3 doesn't, but the F of 3 minus 1 does, and that's why the next element after that is wrapped in another level of list.
Okay, but why doesn't that show up here in any way?
It's like I said, it's the solid edges or sub-expression recursion, and the dashed red edges are the transformation rules.
But there's no because these functions are all of one argument. Is that why this is looking like this? If these functions had 2 arguments, it wouldn't look like this.
Yeah, I think.
Huh. And sort of having one argument is kind of like being trivial with respect to space somehow, I think, maybe. Okay, well, when we've got this labels properly, we can really look at this. This is really good. Okay, Nick, are you ready to do your demo?
Yeah. We wanna go. Are you on sharing?
Yeah, sorry, go ahead. Yep.
So basically the main change here was like for this simple theorem and for simple axiom, it's like previously it was actually treating it as it instead of universal quantifier, it was an existential quantifier. So this is exactly produces a node style proof. It's just the only difference that there exists one here instead of for all.
But is it proving a different thing?
It's proving the same thing but differently. It's like this proof when there is a for all quantifier on the top level for your hypothesis. The default mode is actually to prove it by contradiction. So what it's doing is actually
Hold on. I want to clarify something.
Yeah.
In terms of what find equational proof, like my favorite example for my Boolean algebra axiom. Okay, I want to prove P dot Q equals Q dot P. Right?
Yeah. So
From that axiom. It's the other way around. It's first P dot Q equals Q dot P. It's a center dot. Okay, so now this is the thing. Okay, is that the traditional proof or is that a new proof or what is that?
That's a traditional proof because I haven't used the quantifier here.
Okay, so now put in a quantifier. Yeah. Okay, so that's the thing I thought I was proving.
Now it's much more simpler.
What? How could that possibly be? Okay, show me the proof.
Data set. It's basically just one critical pair lemma that required here.
And show the proof notebook.
Okay, maybe it's
I
am totally confused. Okay,
so
let's
you
try
see the wording. So you see the wording. We would like to show that true equals false. I mean, if we are going to prove a contradiction, we need to start by rewarding that, because we don't want to show that true is equal to false.
Yeah, I know, but there's a much more serious problem. Okay, so right now, I've had for the last 20-something years this proof of that Boolean algebra axiom. Are you telling me that there is a vastly simpler proof that could be given?
well.
I don't really believe it.
You're kind of doubting it right now too, but I think it should be correct because if I.
But it can't be. I mean, that's a very non-trivial thing to prove.
Well, it's not constructive. It's not constructive. So.
What do you mean? But what the heck is it proving? Look, I don't even see the axioms here. Where are the axioms here?
Oh, axiom 1. I guess it's not even required to prove it.
This is nonsense. Sorry. This is nonsense. Q dot P is not generically equal to P dot Q. Right?
Hold on. Got to be used somewhere because there's some non-trivial.
I think this just isn't right. I mean, look, to prove P dot Q equals Q dot P, it takes all kinds of gymnastics given that axiom. Okay, let's do the following. Let's take the original, let's say axiomatic theory of Wolfram axioms. Just let's get the axiom, okay? Just get it explicitly out. Okay, now let's use that axiom, but let's edit it. Okay, just use it raw. Just enter that thing, and we're going to just edit it in some random way. Okay, now put a just change one of the B's to an A or C or something. I don't care what you do, C dot or something. Okay, all right, now let's try again.
It's not using it for some reason. I agree. Just
okay.
But the setup is whatever the setup is. It's just
wrong. Something that's just gone wrong here. Okay, I think we should consider this a bug. But I don't think that proof by contradiction, well, I mean, here proof by contradiction is just doing the wrong thing. But do we have a case where we can see that it's doing the right thing?
You mean where it's actually using the axiom?
Yes.
I guess there's a bunch of those. Like this is the classical one from.
Okay, well, let's see that run. I mean, so
Well, this is the. Well,
I
this
see
is
that's got a
the-
predicate, but
yeah. Well, it's not going to be changed much from the previous results because it's still an existential quantifier in the hypothesis, so it's the same. But if you
Okay.
pick, like,
I have
Boolean
another
logic-
comment. I have another comment I would like to make. Can you open that summary
What?
box?
this one?
Socrates. Okay.
Yes. So this one has not, I mean, these two new fields, variables and constants, has been added. And
Yeah.
how this works is that because this is an equational prover, there is a conversion of these things into an equational language, and that introduces internal variables. Now, I wonder whether we should actually report that we introduce 15 internal variables and whether that's useful or not.
Well, if they show up in the proof, I think it is useful, yes.
Or definitely useful for actually extracting some, for example, a proof function from the proof itself.
But Jose, what's your point? I mean, the fact that we have to introduce these internal variables, I mean, we have to do that even in cases other than, predicates like this, don't we? I mean, I think.
Well, my point is that in a sense, the conversions to equational language is some sort of internal method to prove this. If we had a general first order logic prover, we wouldn't have to do this conversion. Right? So, I mean, I can imagine that we could do different conversions, and then
Yes,
they would introduce different numbers of variables.
Well, I mean, look, we can make different proofs too. I mean, it's just
exactly.
a find equational proof. I mean, it doesn't guarantee to be the smallest whatever.
Right.
And
So-
in general, we can imagine a method where it would end up without generating intermediate, new variables.
Mm-hmm. Right. So in a sense, this is like reporting on how many internal module variables we have created. And so it looks too internal to me.
No,
Well,
no,
would it show up in the actual proof?
Sure, it should be there. There are a bunch of.
Yeah, C1 and all that. See, the fact that they actually show up in the proof, if they do, where are they? There are 15 of them supposed to be.
What the actual variables?
I don't understand. Something's gone wrong here.
Maybe they're not necessarily part of the proof.
Well, but then I don't care about them. I mean, what matters, the fact that somewhere in the bowels of the implementation, it generated random variables, who cares? I mean, it might have generated those on a path that it decided not to take. And that's a distinctly don't care type situation. It looks like it generated one new variable here. Am I right? I mean, that's what we should be counting. And that's interesting to know, it seems to me.
Well, I think this particular case is actually so many variables because I'm counting them separately for each axiom. Maybe that's the problem.
Oh, I see. So they've been renamed.
Yeah. And
So
then
there are a
again,
limited number of canonical names, because in a sense, what we're effectively doing is scoping. Each one of those axioms is really scoped to that axiom. Is that right? I mean, that's going to bite us eventually, but that does not explicitly show scoping.
well, when you just show the axiom on its own, it's fine. You can canonicalize always. But when you feed it into some equational theorem prover, you may want to distinguish that this variable actually came from this axiom.
Well, but look, in general, every axiom will get used many times, and its variables are scoped to within that axiom, and those explicit names will be changed each time it's used, just like module variables, right? Those variable names don't mean anything in any of these axioms. They're always going to get renamed. And the fact that they're called ABC here is just for pure visual convenience, that we can canonicalize them separately. Am I right?
Yeah. Right.
Okay, look, bottom line here, there seems to be some kind of bug. So I don't think, I mean, is there anything else we can look at without resolving that in this stuff here?
You mean variable case or the
No.
like
Look, the basic case is broken. So it's hard to know what we're supposed to look at, right? The basic equational case is broken here. Right. So
maybe
Jose
that's
was
the
saying
problem.
he doesn't like the fact that it's proven by contradiction, but the fact is it isn't proving anything because it's broken.
Okay.
Right. So we can't really look at it without resolving that.
I'll dig into that. It's just
But
I'm pretty sure that the proof, whatever proof is set up, it's like we're trying to prove this new hypothesis, like true equals false, and with the new additional axiom, that's what we are doing. If it somehow managed to do that,
But it didn't. It didn't. This has done nothing, right? It can prove it. It proved it even in the case where we just changed the axioms to make it nonsense. Right? It just
well,
sort of blindly
that's
says I can prove anything.
maybe just the nature of this particular hypothesis. I don't know.
But it's
What-
clearly wrong. I'm sorry. It's you know, look, we've got an axiom here that asserts something. Okay, look, why don't we just say, I know what we want to do here. We just just give an axiom system for which this clearly isn't true. I don't know, P dot P equals P. Try and prove that. P dot P equals P.
P dot P equals P.
Yeah.
Hold on. Yeah, I think
It's nonsense. I'm sorry.
yeah, maybe this one is broken because
It looked like, by the way, there was some confirmation failed in the proof
yeah.
function.
So this one I can't trust because the proof function was also wrong.
Okay, look, I think it's just a bug somewhere. I don't think we should spend a lot of effort on it. But I want to come back to what the issue of principle, which I don't think we can resolve here, which was you are trying to rearrange these proofs to be proofs by contradiction. I don't really understand why.
No, I'm not doing it explicitly. It's what Waldmeister doing. It's like in its code, it's when your hypothesis is not grounded, basically when it has variables, it's doing it explicitly there. It's adding this additional axiom and trying to prove true
Okay,
equals.
something has gone wrong. So I think we need to resolve what's gone wrong before we can continue this discussion. But is there any further, I mean, and whatever it's doing, it was obviously made to do something which seems to have been almost correct previously, but for some bugs. Whereas now it seems to have gone completely off the deep end. So I mean, what can we do usefully here on this? I think, Jose, is there anything else you want to bring up here? Because I just don't think we can discuss this until it actually works.
I agree with that. I suggest that we add an option so that users can choose which type of proof they want, so that
I like
in the future, not everything relies only on contradictions.
Yeah, I think that's fine. I mean, I think.
So, by the way, I mean, to ask a more naive question, I mean, if the reason is we're doing these proof by contradiction because that's how Waldmeister does, for all statements, basically. I mean, is there a reason why we don't try and make some connection to some other first order logic prover?
I don't think this is how, I think this isn't, something's gone wrong here. Okay, because this is not, for the last however many years, we've had a thing which doesn't do proof by contradiction. So we clearly have a way to do that. So something is confused here. But, it took significant effort 20 years ago to, and it leverages good software engineering that was done, by the group that developed Waldmeister and so on. I think it is non-trivial to connect to other things. And these things require more babysitting than you expect. I mean, it's something we could investigate, but I don't see the point at this moment. I think it's more interesting if we have fundamentally different kinds of proofs. Okay, there's some stuff that has to be resolved here. But the thing that we had really wanted to talk about is how do we take proof objects and make them be more useful? So, I mean, Nick, you have a proof function there, which still looks kind of impenetrable. Right. I mean, this is what we want to clean up, because this proof function is also like an evaluation graph, is it not? I mean, there's a very close correspondence between a proof graph and an evaluation. I mean, the proof graph and the evaluation graph, is there not? In other words, what this is doing is it's saying, you know,
Oh, yeah. It's like each result of each lemma is constructed here explicitly.
right. So that's what I'm saying is what, I mean, so that's what we're trying to represent in the evaluation graph. We're trying to do the exact same kind of thing. So what I'm hoping for is that we can have a unified approach to showing kind of the innards of a computation. If that makes sense. So that they're composable, and so we can do computations on, you know, what we want to do is meta computations on the computation. Am I making sense? Right. So we have either a path that we either have the evaluation graph. Look, the vision is obviously this. We've got, in the past, we've only been interested in input output. Now we're going to actually display the evaluation graph. We're also going to display, but the evaluation graph is merely a single way evaluation graph. It is one path through a multi-way evaluation graph, except that we have chosen a particular evaluation order so that we make it single way. In the case of a proof object, there is no, the choice of which, I mean, this is a single way, computation, but which single way computation it is not chosen in the same way that we would choose it in standard evaluation, where it's just, whatever it is, leftmost, innermost, or whatever, innermost, leftmost, whatever it is. What is it actually? Is it leftmost, innermost? I think it is. Does that make sense? It's some other, I mean, just as, and this relates also to the naming of traversal orders, right? Because we're talking about leftmost, innermost, to make a proof, if we were to represent every possible choice by some integer or something, the proof might be 1734824 or something, showing at each branch where do you go in the multi-way graph. Whereas in some sense the standard evaluation order is like 11111 in the multi-way graph. Is that making sense to people?
Yep.
So, I mean, what we want is a uniform, what we want to be able to do, both for proofs, we should be able to make the full entailment cone, which is the full multi-way graph. For evaluations, that's what multi-evaluate does. It makes the full multi-way evaluation graph, which then by, we can look only at that particular path that corresponds to ordinary evaluation. The theorem prover is finding, it's like find replace path, which I keep on wanting us to really, really get implemented. It is finding a particular path. And, again, we can make an evaluation, we make a representation of that evaluation process, aka a piece of the evaluation graph. Right. I guess that this is again a complete evaluation graph of the non-multi-way kind. Is this making sense? Let's go back to my screen.
By the way, I put some code in chat to fix the trace graph output.
Oh, good. Okay. Oh, lovely. Okay. Well, that was a bit more complicated than we expected. Okay, so let's say f of 2, for example, here. Oh my gosh. Okay, so now if I say f of 2 with f vertical bar plus here, what am I seeing here? Okay, can I get it to just do f of blank, not do the f's themselves?
Yeah.
Can I just do that?
Yep.
And what do I do here? Do I say verbatim or what do I say? Oh, actually, if I just say underscore plus, that should work.
Yeah.
Okay, now I'm super confused. I just don't understand this. How did it go from f of 2? Okay, it's got this. Now, why is it not branching there? It's sub-evaluating 2 minus f of 2 minus 1.
You got rid of the other branches with the pattern.
Why? Because it's still got an f there. I don't understand. It should have a place where the evaluator has to dig in.
The only argument of that expression is the one expression that you see there. If it was 2 arguments, then there would be another branch.
So are you telling me, I mean, if I did the same thing for Fibonacci, I see that there's a plus there that is, but I don't understand. The plus will have 2 arguments in plenty of places. I am totally confused. Okay, I am, well, I mean, this is, at least I'm less confused now because this is what I would have expected it to do, more or less. Let's just look at the ordinary Fibonacci piece. Oh, well, that didn't help there. Okay, let's see if I understand this. Why does it even show that one? Okay, fib of 5 evaluates to fib of 5 minus 1 plus fib of 5 minus 2. What's that line there? That's showing an evaluation, a sub-evaluation.
That's showing a transformation rule being applied.
Why isn't there something shown here as a transformation rule? Fib of 5 going to fib of 5 minus 1 plus fib of 5 minus 2. Why isn't that a transformation rule?
Get rid of the second argument. So there you see the transformation rule from fib of 3 to fib of 3 minus 1 plus fib of 3 minus 2.
Okay.
You didn't include plus in the pattern last time, so that node was skipped. So you just had the direct edges to fib of 3 minus 1 and fib of 3 minus 2.
Okay, so if I go here, underscore fib or underscore plus, and I say fib of 5. Okay, that's an evaluation. That's sub-expressions. Sub-expression. Oh gosh, this is this crazy pullback business that happened there, right? Which we don't have a great representation for. You understand what I'm saying? It nested, it
Right.
recurses down to this, and then it pulls back to that.
Mm-hmm. Which is clearer without the pattern, but I agree it's very hard to tell what's happening.
Nick, do you have a comment about this? I mean, how does this relate to the other kind of, or James for that matter? I mean, the things that we've been doing, this is like super obscure. In combinators, we had these weird, oh gosh, what were we calling them? Pseudo, oh my gosh, what the heck was I calling them?
I guess another problem is
I remember
it's
this.
not clear if that's a deconstruction or a reconstruction. happens to be a reconstruction.
Well, right. This is a going back up. Okay, this line, this is not going to cut it, right? That line there is the same as that line there.
Mm-hmm.
Because this is a drill down and this is a
Go back up.
a build back up.
Mm-hmm.
So, oh gosh, how do we represent this?
We talked about maybe flaring the edge.
Yeah. But what really is going on here? I mean, in other words, in the process of evaluation, what was I calling them? I was calling them pullback pseudo events, I think, which is just the most disgusting. I mean, even that very name tells you that it's a crazy concept. Again, Nick, can you comment on, I mean, in terms of an event graph, this is clearly an event. That red thing is clearly, you could put an event here.
Yeah.
But all of our evaluation graphs are one-to-one events. They just take one expression and turn it into. I'm really confused here. Anybody help me? I mean, okay, do people at least understand why I'm confused? That this is drill down, this is pull back up.
Yeah, and that is confusing when you have a second argument pattern, because it removes a bunch of nodes from the graph that would otherwise clarify what's happening.
Well, let's see how it clarifies. I mean, if it clarifies, what else do I have to include to help clarify?
Just remove the second argument.
I know that, but it's going to then get very, very, very complicated. Right.
But
So
we're not going to know until you remove it. I mean, it seems like the unintuitive thing is the fact that the F is disappearing and then like coming back, if you know what I mean. Like there's no,
Right.
it's like it's pulling information out from the ether.
Yes. Right. And,
Yeah,
and
so
perhaps
I guess the symbol fib would be another thing to add to the alternatives, not just blank fib.
okay, but hold on. What happened here? So where was the pullback happening here? This fib of 4 minus 1.
So you see it's got these two branches.
Hmm.
One is trivial, it just has the fib. And then the other branch is the 4 minus 1 becoming 3. Right? And then those two things feed into the fib of 3.
Right. So the problem was that left branch that is just fib wasn't included because it doesn't have head fib. It has head symbol.
Mm-hmm.
Right. Okay. So let's just try for here.
It's 4
What
and then
happened?
going straight into fib of 3.
Okay. So let's say or fib.
Do like blank integer.
Why do I want blank integer as well?
So here you see you have a 4 minus 1, but you never see 3 by itself anywhere.
Right. But the problem before was in here, all I see is 4 minus 1. I'm not seeing the carrying. This has deconstructed itself down to fib of 4 minus 1. And that deconstruction is visible here. See what I'm saying?
Yeah.
But that deconstruction is not visible in the other case.
Right.
But where's 3?
All you can infer from the other case, assuming you can tell that it's a deconstruction edge, is that 4 minus 1 gets evaluated as a subsidiary evaluation, but you don't see what it evaluates to. You just see the end result is fib of 3.
Okay, but I want to remind us, okay. You know, Nick has proposed this formalism where everything is a hypergraph. Essentially, what's happening here, the confusion is we are used to seeing expressions as single unified things. But what's happening here is as we look more granularly at how the evaluation happens, every expression is shattered into its subpieces. And the difficulty is, I mean, it's the same difficulty. Okay, so we've got the two different difficulties. Actually, Nick, I don't understand. In your proofs, you have the same reconstruction issue, do you not? You can end up doing a subtree transformation, which then has to be pulled back into the full tree. Is that true?
When I'm doing a proof function?
Yes.
Do you mean?
Yes. You can make a transformation of a subtree, and the way you're representing that is you're saying, I mean, you're then going to use that subtree that has been transformed, and it's going to get pulled back into a bigger expression, is it not?
No, it's kind of straightforward to just do replace that. That's what it means to pull back a subtree.
Fine, but then okay, but then can we think of this doing replace that? This is doing replace that as well. I mean, it's doing replace that of the first part in fib of 4 minus 1 of 4 minus 1 with 3. So in a sense, these edges, which here are just shown as a single edge, in the proof object case would be annotated by the part number of the replace that is operating there. Am I correct?
Yeah, when you have part numbers, it becomes very easy to see what's going on.
Right, but the point that I'm making is the evaluator is a giant festival of replace that's, basically. It's just doing a bunch of replace that's in a particular order. But right now, we are not recording where those replace that's happen. Instead, here, we are recording the lineage of that replace that was the result of a sub-evaluation of this thing here. Whereas in the theorem prover, you are explicitly recording the part numbers at which the replace that's occur. Am I right?
Yep, correct.
But one of the issues with that is the part numbers are not very stable. And as soon as the transformation has been done, it's new part numbers. I don't know if that's an issue or not, but I mean, it tells you for every step, it tells you you're making these. I mean, we could do the exact same thing here. We could, if the, think of the evaluator as a super axiom called eval, let's say. Then at each place here, we could be saying that edge there is replace that of, or maybe map out if it's just using eval, but it doesn't really matter. Replace that effectively on fib of 4 minus 1, part 1 with what you get from replacing with eval. Am I right?
Yes, and I just want to add the caveat for the standard evaluation sequence. If you have non-standard evaluation, then it's not a replace at. You get arbitrary deconstruction and arbitrary reconstruction. Not just replacing a sub-expression with a new one.
Well, you mean eval actually does something non-trivial. It runs internal code on the whole object.
Yeah, so you deconstruct the expression. Here you're deconstructing it into just the things at level 1. But you could deconstruct it into just totally arbitrary expressions that have nothing to do with the original expression structure.
What would make you do that?
Let's say you had a function with a hold attribute.
Okay, that's the case. But the main point is with a hold attribute, the internal code is gulping the whole innards of the function without having done sub-evaluation.
Right, and the point is there will still be subsidiary evaluations, and they'll still be denoted exactly the same way.
They'll happen somehow mediated by the internal code in some way, which is much more obscure.
Yeah.
Okay, that's a different case.
So there's two categories. There's either the evaluation of an expression at level 1, or totally anything with non-standard evaluation.
Nick, you were going to say something.
I was going to say you can still record all the part numbers for the inputs and how you do the reconstruction. Basically, when you do the reconstruction, when you do evaluation, first you extract some part numbers, do some computation, then you construct it into a new expression with new part numbers. So there's still information there, even for arbitrary.
Right. I just want to go back to our big roadmap for a second, yet again. Although okay. So the big roadmap talks about, the pattern stuff. We've talked about that a little bit. I understand. I think we should be thinking carefully about what we actually want here and what's going to be used for. The evaluation graph. Well, we've got this composability issue here, and we've got these issues about understanding pullbacks. So there's some questions there. Yeah, I mean, we really do have a roadmap, and we really do need to actually get implementing a bunch of these things. I mean, this one is, again, we've talked about this a million times. This is the multi-way case where we're finding a single path. And where, find replace path, and this is a point for find replace path could in principle take a traversal order option. Find replace path becomes stupid if it takes a traversal order option, in the sense that then you're just telling it the path. Does that make sense to people?
Of course, yeah.
Right. And so, I mean, although you might want to partially tell it the path, and you certainly want, at each decision point, you can imagine it, scratching its head and using machine learning or something to decide which path it should try. Is that something we think we can parameterize, or is it going to end up with something like the horror of breadth first search, which is not unrelated to find replace path?
Well, we can leave it as an option, like what basically supply a function that decides where to move next. And
based on what?
Based on your current history. And
so it's like a fold type thing where it knows what the path has been so far, and it's asked, where would you like to go next?
Yeah. And maybe not just a single path, but also all the alternatives paths that it took, because it maybe just was wandering around.
Well, it also may be that it already tried taking future paths, and it's now backtracked from a future path, and this is the only, and there's no point in retrying a future path that it already took.
Yeah, basically a whole previous graph, the graph at this point that is constructed.
Well, hold on a second. I mean, potentially include its complete exploration graph. What the heck is an exploration graph? I mean, in other words, I understand the final path and I understand the full multi-way graph, but what is this exploration path? Is it a partial multi-way graph?
Yeah, I don't see a difference.
So it's a subgraph of the multi-way graph.
Yep.
I think that's right. Yeah, I think that's
maybe
right.
Not just a subgraph, but like you have like a sub, because you have to start from the root. It have to include the root.
Okay, fine. I mean, which is basically a subgraph that includes the root.
Yeah.
I mean, we're not saying it's any subgraph. The exploration graph is not any subgraph, but it is a subgraph, is it not?
Yeah.
So here's an interesting point. If you've got an exploration path, let's imagine that you feed in. Well, okay, so composability of find replace path is ultimately, it's a graph union of exploration graphs. I claim. The full multi-way graph is a graph union of exploration paths, exploration graphs. Just like for a proof object, one can imagine, well, what the heck does it look like? What is the composition of two proof objects? In a sense, that would be a proof object is like a path. That would be you're going from this root set of axioms to this theorem, and then you go on from that theorem to another theorem. I mean, is that the question is what kind of composability is there for proof graphs? What kind of composability is there for evaluation graphs?
There is some.
What's that?
It exists, basically. It exists. I don't
Some
think
kind of composability.
Yeah.
Right.
It's not
But
trivial, but it is there.
Right. But okay, the thing I keep on pushing for is a unified treatment of the evaluation graph and the proof graph. Because I think they are the same thing. They're both, you know, single way slices of the multi-way graph. The evaluation graph might seem like a more natural one because it is just going down the leftmost, innermost evaluation path, whereas the general proof graph was carefully found, to navigate down to the result. I just want to look for a second at your.
Also, the difference between evaluation graph and proof graph is how is it? It's a cumulative, right? So you can imagine what evaluation would look like if you would generate new down values as it evaluates.
It's like everything is memorized.
Yeah, something like that. Yeah.
Well, that's interesting. Yeah, go ahead.
It's just not memorized. You have to. It's like computation. You generate new computation. It's not just memorizing. I think it's more than that. New rules, new down values as rules, and not just remember the output.
But I think you mean new down values of the form f of x. No, that's because, okay, in an ordinary evaluation, everything is a literal at the time it's evaluated, or almost, unless you're constructing code on the fly. Whereas in the case of a proof, you are constructing the statement x blank dot y blank equals y blank dot x blank, which can then be applied as a pattern to other things. Whereas that's not something you do in ordinary evaluation.
Yeah, exactly. That's what I say. You can imagine what would it look like if it actually did. It's a different.
Well, if it
thing.
proved intermediate theorems in the case of, if it said, I've just got the straight evaluation, but I will be able to evaluate faster if I prove this intermediate theorem. Like if the evaluator said, nest, append, or fold, some kind of fold of append, that's equivalent to a join. And it could just do that transformation internally. And you're claiming that that's what the theorem prover effectively is doing by generating lemmas. Generating lemmas causes it to jump ahead and not go through every step, whereas the evaluator does not have a mechanism to do that. The evaluator has no way to prove micro lemmas, so to speak, that allow it to jump ahead.
I guess, unless there's some optimization. But in general, no.
Right. I mean, but that's what you're saying. That's what the proof object does manage to let one do. So it's an interesting thing, as you say, to think about what would happen if you were able to do that in ordinary evaluation. We should wrap up here, but okay. I mean, clearly the main thing that needs to happen is just actual progress on these pieces of implementation, and where there no doubt will be things run into that are difficult, and that's what these meetings are about, is to try to resolve those. Okay, anything else we should make sure to go over right now? Nope. Okay. Thanks, everybody. I'm glad to see this trace graph. Do Ian, you will put in that fix, right? So that we get trace graph really in 13. Yep. Okay.